waves rather than a stationary pattern. Now, stationary patterns occur in many situations, but also these time-dependent patterns occur in many situations. This was a real surprise in 1991 to find where if you take a box of fluid and you heat it from below so that you would get convection, instead of getting convection rolls, convection cells that are arrayed like stripes or in a hexagonal pattern, this is a picture looking down on this box of fluid, and the investigators, Bodenschatz and others, found that you get spirals which rotate. So it's a rotating spiral pattern. Or in a biological system that's very well studied, because this is a frog egg, xenopus, and it's fairly large. This distance here is about 1 millimeter, so it's easy to study and look at it in a microscope, whatever. And you see that there are rotating spiral waves in this frog egg. And these colors represent concentration of calcium in this system. Now, we can have electrical waves as well, and electrical waves which are important to everyone in this room are those which originate here at the SA node in the heart. And then you have, this is a pacemaker, you have these pacemakers, SA node, AV node, and you have the waves propagating out along these bundles, and then through these fibers, Purkinje fibers. And that's the normal rhythm, normal wave that makes the heart have its rhythm. But there are situations where you get on the surface of the heart or within the heart waves. These waves are not just emanating from the pacemaker, but something which is sustained is a spiral which rotates. Now, this is actually a mathematical model of a dog heart where you get these spiral waves. And this is a real rabbit heart where they put electrodes on the heart to measure these electrical waves, and you don't have a very clear picture, but there is a rotating spiral here. Now, these waves are not the waves you want. This is what you want. Because this leads to fibrillation, irregular heartbeats, which don't produce much blood flow. And these spiral waves, which can break up into smaller spirals, are responsible for more than 100,000 deaths per year in this country. So there are many people studying these spiral waves in actual hearts and also in model systems like the chemical system, because the mechanism in the description is the same whether it's a complex heart or whether it's a simple system. And they believe, and they're working on pacemakers, which could interrupt this spiral wave with a very small interruption and make the heart go back into its normal rhythms. Not a big interruption like in a defibrillator, where you have an enormous kick in the chest, but some pacemaker which with a very small disturbance of this wave, very small, but a smart pacemaker that has a little chip in it that will detect this waveform and be able to, just at the right time, interrupt it and return the heart to the regular rhythm. I mentioned before you get waves, and you've seen waves on the surface of a cup. When you move a styrofoam cup or something across the table, you see the waves on the surface. If you oscillate a liquid layer up and down, you can get the formation of waves. If you oscillate it with small amplitude, then the surface will remain flat. But if you oscillate with a larger amplitude, beyond the critical value of oscillation amplitude, you could get the waves forming. And the waves, if you look down from above, down at the surface of the fluid, can have different patterns. This is a hexagonal pattern. Here's another one, the same hexagonal shape, but a different kind of waveform. Here we have stripe pattern. Well, 2 years ago, Robert Deacon in our lab wondered, thinking about cornstarch as another fluid that we could put in a container and shake it up and down like we shake water and study the waves on the surface of water. But we all know cornstarch has some peculiarities. When you stir it, if you're stirring batter in the kitchen, you stir it slowly, it's easy to stir. If you try stirring it fast, and the cornstarch is pretty highly concentrated, you try stirring it fast, then it becomes hard to stir. It's like the batter becomes thicker. The cornstarch itself is made of small particles. They're about 10 micrometers typically in size. So we took a layer of cornstarch and shook it up and down, and I'll show you what was observed, I hope. Yes. So this is the layer at rest. The container is not being shaken, just showing you that it's an ordinary fluid. It's a little bit thick, but it's just like you might stir it in the kitchen in a pot. Now we can start vibrating this layer up and down, and here the vibration amplitude, that is the maximum acceleration, is increased from 0 up to 30 times the acceleration of gravity. Here's some small acceleration, and you see the waves, which are just like the waves you would see if you have waves in a coffee cup. And these are not determined by the boundaries. These are intrinsic property of the fluid. You can see here they're pretty irregular. Now, the first thing that was observed that was unusual was that if you make a little hole in the fluid, instead of that hole disappearing, as it would if you had a cup of water, you poke your finger in the cup of water, you remove your finger, the hole that would disappear, this hole persists. You can make a big hole and it will decrease in size, and then find a particular size and just persist in time. If you had a small hole, it would grow till it reaches this size. The hole likes to be a particular size. Now, out here, you have the waves that are like the waves you would have in water. And you see around the hole, you have a little rim. So there's a little rim. Now, looking from the side where we have 2 of these or 3 of these holes, you can see they interact in a very dynamic way with one another. So there were some articles about this in newspapers. They call this holy water. Now, if you make the acceleration of the container larger, the holes are no longer stable as holes. The rims start to grow. And here, these projections, these pieces go up to a height several times the thickness of the layer of cornstarch. This is ordinary cornstarch, nothing special. So we know the equations that describe this system. This is a problem we haven't worked out mathematically. Okay. So what happens if we force a system further? If we go far beyond the point at which patterns first appear, then we can get some very complex patterns. We take the Earth's atmosphere, where it's strongly forced by the light coming from the sun, a large amount of radiation from the sun, and you know that we have very complex patterns of clouds and weather. Or if you take many examples from biology, they're extremely complex. If we had a system which was in uniform conditions, which I said is not the subject of tonight's discussion, there is a systematic way for calculating the state of the system. You calculate a quantity called a free energy and find when it's a minimum. But there is no general systematic way for calculating when these complex patterns will form and what kind of patterns they will be. So in the absence of fundamental theory, we are exploring, and many people are exploring, the behavior of systems by doing laboratory experiments and by examining simple mathematical models on a computer and solving these models on the computer, or sometimes more complex models, the full equations. So I want to show some examples. And it's the only equation, so for those of you who have or who are averse to equations, just hang on for a moment. But I think it's good to look at one equation just as an example. And suppose you have a very simple chemical system of the type that was studied by Turing, where you just have 2 processes. A reaction, say species A reacts with species B. So you take 1 molecule of A and 2 of B, and they react together at some rate K to form 3 molecules of type B. In a liquid solution, they would have some concentration, say A at position R at time t, and concentration of species B would be this B at time position R and T. Now the rate at which A would increase would depend on how fast it diffuses, spreads out, like a drop of dye spreading out, and then A is being consumed by this reaction. Here, there's no A on the right-hand side, so it's being consumed. That's a minus sign there. How fast is it being consumed at a rate K? And the consumption rate will be proportional to the concentration of A, and A requires 2 of molecules B to form this 3B, so that's minus KB squared. And then to keep the system going, you have to keep feeding chemicals. And similarly for B, except we're producing B, so we have a plus sign here. Now this is a pair of equations that one can put on a computer and study the solutions for different values of these constants that characterize the system. The rate at which A diffuses, the rate at which B diffuses, the reaction rate for the reaction, and these feed rates and the concentrations in the reservoirs. And that was done for this particular system by scientists at Los Alamos National Laboratory, John Pearson, and he found for different values of those parameters, so just taking different values of these parameters, these different patterns. And some of these are like those I've discussed. You have stripe patterns or spot patterns, which are time independent. They're just stationary. Here's another spot pattern. But he found something interesting which had not been seen in any other studies of models on computers or in any laboratory experiments. These are spots that change in time. They grow and interact, and here's what he found. So you have a concentration, say, of one species, which is high here. That's a spot of that species. If you look at a later time, it will have grown, and you can see it starting to divide, and then you have a pair of spots, the daughter spots here. If you look at this daughter spot, it grows in later time and grows further and ultimately divides. I had a very good student who was working on a chemical system at that time, and he went into the laboratory and began to play with parameters in the experiment, and in a very short period of time, he found something similar in a reaction which has nothing to do with this simple model. This is a very simple system. The real reaction that he was studying has these chemicals reacting, and they produce many intermediate species. So in the chemical system that he was studying, he had maybe 30 different chemical species, but they show similar types of behavior where the spot here at time t equals 0 is a single spot, but it grows. Here's it 4 minutes later. It's growing, and then it divides into 2. And this daughter spot here begins to grow, and it divides. So you have these self-replicating spots. And this is a video which shows this process. Let's look at this spot here. Basically, the spots grow by eating, the blue spots grow by eating the yellow. Now here, this spot is competing with its neighbors and starts to shrink here because of the shortness of food supply. And it divides, and you can watch, say, this daughter spot, which is about to disappear. And sometimes the spots die, but this one now has a lot of food, so it's growing fast, and it will grow until it competes with its neighbors. And here you can see it starting to compete with its neighbors and this neighbor over here, and it grows and it divides. So this was something that was found in a particular simple mathematical model, then in an experiment, and now has been found in many different systems. It's a common type of behavior for these chemical reactions. Now I want to turn to a different type of system, one that consists of particles, like grains of sand or garlic tablets or whatever, some particles. Now, a granular system is different from a liquid or a solid. It's sometimes like a solid. You can walk on a beach. The sand will support your weight, but you can also take a bucket of sand and pour it, and that would behave in a way similar to a liquid. But we don't have fundamental equations that describe a granular system in the same way we have the equations which are well established for solids and liquids. So we want to understand more about the behavior of granular systems by doing experiments. One kind of experiments that is done is to just shake the grains up and down in a container. And we shine light from the side and look from above with the camera So you see some grains are higher in the air than others, and those are lit up. So when you look in a picture taken from above, you see regions which are bright and regions which are dark, where the grains are not illuminated. Now, this is what happens when you shake hard enough. If you shake with a small amplitude, you get no pattern. The layer remains flat. But here you see when you shake hard enough, you get these peaks forming. You can see that there are waves. And when you have a wave at one oscillation, the next oscillation of the container, you have a little valley. So you go back and forth with sort of sloshing of the particles. Now, if we take a big system and look from above, as I just mentioned, and shake it with a certain frequency, 23 times per second, and with the amplitude of shaking, which is 2.6 times the gravitational acceleration, we get this very nice pattern. One of these dots here has maybe 100 or 500 grains of sand. So you don't see the individual grains of sand, but if you take a small region and blow it up, you can see the individual grains in this pattern. Very beautiful pattern. And if you look at one of these peaks from the side, you can see the individual particles. So here are the particles. Actually, in this experiment, these particles are bronze balls, and they're 0.2 millimeters in size. But you get the same patterns if you shake sand. Okay. And if you change the frequency of the shaking, instead of getting this square pattern, you can get stripes. And notice that the pattern is not influenced by the side walls. The other container was square. Here we have a circular container, and the pattern is uniform within the container. It's only affected by the walls, very near to the walls. This is when you shake at a certain amplitude of shaking, but if you increase that shaking amplitude, either with a square pattern or stripe pattern, you go over to a pattern which is hexagonal. This is a honeycomb pattern, or here's a dot pattern, which is hexagonal. Now, I said we don't have well-established equations like we have for a fluid or a crystal, but we certainly have Newton's laws that describe particles and how they interact and how they behave when they collide. So if we apply Newton's laws to a large number of balls on a computer, we can calculate the motion of the balls. So they collide, and when they collide, they conserve momentum. And they're also spinning, and so they conserve something which is called angular momentum. Between the collisions, they just are moving under the influence of gravity, so they move in a path that's a smooth curve like a baseball would move, a parabolic path. So we can consider a container with many balls in it and calculate what the pattern would be for a particular frequency, say 15 oscillations of the container per second at a certain amplitude of acceleration. And here's the result from the computer simulation work done by Chris Bison, and you get this nice pattern. And here's an actual picture from the experiment, and you can see the patterns are the same. Not only do they have the same form, it's the same spacing, same size pattern. And if you go to higher frequency, the pattern changes, both in the experiment and in the simulation. So this gives us, starting with Newton's laws, some grasp of these patterns, and we can then consider many other problems. And grains are used in many industries. We can think of the chemical industry as supplying chemicals in a bottle, or at least I do, I'm not a chemist, but in a brown bottle. But most of the products supplied by chemical industries are in the form of grains. 2/3 of the products of DuPont are supplied in granular form. And so there are questions about how do you separate grains of different sizes? How do you mix grains together thoroughly? Suppose you're a pharmaceutical company, you have an inert ingredient, you want to mix in it some active ingredient and make tablets which are uniform in the dosage. The only way that that is done is through some rules of thumb that the industry has developed, not through some fundamental understanding of physics. So we would like to try to improve our understanding of how granular systems behave. Now, what happens if you consider a system which is pushed very hard? In the case of the flow between concentric cylinders, instead of rotating a few rotations per second, suppose we rotate the cylinder 100 times as fast. Does the pattern disappear? Does it become very irregular? No, the pattern actually persists. Even though the flow is turbulent, you have some pattern that is still present. You can see these horizontal lines. Although the flow is irregular, you still have some order in the system. Now, if you look on a larger scale, take the atmosphere, which is strongly forced by the sun. You know the flows are very irregular, but if you look at a weather map, you see that there is some structure there. Here's the North Pole now, looking down from the North Pole, and of course this is the North American continent, and I don't need to tell you what this is. And you see on this map, taken at on a particular day, that you have a flow in the atmosphere that's a jet that goes all the way around the globe, the jet stream. And you have vortices which rotate in one direction or the other direction. These are high pressure and low pressure systems. So you have well-defined structures even for a system that is forced very far from the uniform state. Here's probably a familiar picture. It was taken now a number of years ago by Voyager 2. You have the planet Jupiter, and you have jet streams on Jupiter. These are the jets. And Jupiter has no landmass like the Earth, so the jet doesn't have the wiggles that the jet stream does on the Earth. You have these